September 10th, 2019. Amateur astronomer Gennady Borisov discovers something impossible. A comet from another star system, screaming through our solar neighborhood at 110,000 miles per hour. Scientists track it, study it, name it 2I/Borisov. Then, on March 3rd, 2020, deep space telescopes detect something that makes every astrophysicist's blood run cold, a massive energy pulse. From Borisov, aimed directly at Jupiter. Within hours, observatories worldwide scramble to reposition. Space agencies demand answers. And one question burns through every research facility on Earth. Was this natural? Or was something out there trying to communicate? If you're hooked already, and trust me, this gets even wilder, show some love by hitting like and subscribe. But only if you're genuinely into these cosmic mysteries. Your support means I can keep bringing you stories that'll keep you up at night. Quick question, where are you watching from right now? Drop your location in the comments. I'm curious who's on this journey with me tonight. Now, kill those lights, settle in, and let's dive deep. Because when Borisov first entered our solar system 16 months earlier, nobody expected it would challenge everything we thought we knew about interstellar visitors. Because when Borisov first entered our solar system 16 months earlier, nobody expected it would challenge everything we thought we knew about interstellar visitors. Let me take you back to October 2017, when humanity got its first taste of cosmic tourism. An object designated 1I/Oumuamua, Hawaiian for scout or messenger, blazed through our solar system at 196,000 miles per hour. Astronomers had exactly 11 days to study it before it disappeared forever into the void. 11 days to photograph something that travelled for potentially millions of years just to pass us by. And what they saw kept them arguing for years. A cigar-shaped object, tumbling end over end, with reflective properties that shouldn't exist on any natural space rock. Some scientists claimed it was accelerating without any visible propulsion. Others insisted it was just outgassing, frozen gases heating up and pushing it along. But nobody could prove anything because it was already gone. Now, here's the thing about interstellar space and day. It's not just empty. Between star systems, you've got what astronomers call the interstellar medium, a soup of gas, dust, and frozen debris that's been wandering the galaxy for billions of years. Most of it, leftovers from planetary formation. When a solar system is born, gravity shapes planets from a swirling disk of material, but not everything makes the cut. Some chunks get flung outward by the gravity of giant planets like Jupiter or Saturn. They're ejected, cast out into the darkness like cosmic exiles, doomed to drift between stars forever. According to a 2018 study published in the Astronomical Journal, our Milky Way galaxy alone could contain trillions of these interstellar nomads. Trillions. And statistically, dozens pass through our solar system every year. We just never see them because, well, space is incomprehensibly big and these things are incomprehensibly small. That's what made 2I/Borisov so special. On that September morning in 2019, Gennady Borisov wasn't hunting for alien artifacts. He was using a telescope he built himself, a 0.65 metre reflector at the Margot Observatory in Crimea, just doing routine comet observations. Then he spotted it, a fuzzy dot moving wrong, not along the ecliptic plane where our solar system's objects travel, but at a sharp angle, coming in from above. He tracked it for a few nights, calculated the trajectory, and realised his hands were probably shaking when he sent his data to the Minor Planet Center. Because the numbers didn't lie, this thing was moving on a hyperbolic orbit. You know what that means? It means it's not gravitationally bound to our sun. It's passing through a tourist, a visitor. Only the second confirmed interstellar object in human history. Within 48 hours, telescopes worldwide locked onto Borisov, the Hubble Space Telescope, the Atacama Large Millimeter Array in Chile, the Very Large Telescope in the Chilean Andes, NASA's Infrared Telescope facility in Hawaii. This wasn't just another comet, this was a messenger from another solar system, and scientists had maybe 6 months to study it before it swung around the sun and left forever. Do you have any idea how rare this is? Imagine you're studying marine biology your entire life, only seeing fish in your local ocean, and suddenly a creature from the Mariana Trench shows up at your beach. That's what Borisov represented, a sample of another star system delivered right to our doorstep, and the data absolutely fascinating. Spectroscopic analysis revealed that Borisov was expelling massive amounts of carbon monoxide, about 570 pounds per second. For comparison, typical comets in our solar system release mostly water vapour and a bit of CO, but Borisov, it was CO dominant. A 2020 study in Nature Astronomy suggested this meant Borisov formed in an extremely cold region of its home system, probably far from its parent star, where temperatures were cold enough to freeze carbon monoxide solid. We're talking below negative 400 degrees Fahrenheit. This thing came from a deep freeze that makes our Oort cloud look tropical. But here's where it gets even more intriguing. The comet's nucleus, the solid core beneath all that gas and dust, measured about half a mile across. Smaller than most comets we're used to, but not tiny. Its coma, the fuzzy cloud of gas surrounding it, stretched approximately 93,000 miles wide at its peak. And the tail, over 9 million miles long, blown back by solar wind like cosmic hair streaming behind a motorcycle helmet. Images from Hubble showed it looking almost perfectly normal, if you can call a visitor from another star system normal. Unlike Oumuamua's bizarre cigar shape, Borisov looked like, well, like a comet, familiar, almost disappointingly ordinary. Some journalists wrote, scientists actually loved that ordinariness. Dr. Stefano Banulo from the Armagh Observatory in Northern Ireland said something I'll never forget. The presence of 2I/Borisov has provided the first opportunity to study a pristine comet from another planetary system. Pristine. That word matters. See, comets in our solar system have been cooking under our sun's radiation for 4.6 billion years. They've been altered, weathered, changed. But Borisov spent potentially hundreds of millions of years in the frozen void between stars, unchanged, unaltered, a time capsule from another world. Think about what that means for a moment. Every atom in that comet formed around a different star. Maybe a red dwarf burning cold and slow. Maybe a blue giant blazing hot and fast. The water molecules, the carbon monoxide, the dust grains, they condensed from a nebula that had nothing to do with our sun. When you look at Borisov through a telescope, you're not just seeing a comet, you're seeing chemistry from another corner of the galaxy. You're seeing proof that planetary formation works the same way everywhere, that the laws of physics don't change just because you're 30 trillion miles from home. Researchers traced Borisov's trajectory backward, trying to figure out where it came from. The math suggested it originated somewhere near a binary star system in the constellation Cassiopeia, about 13 light-years away. But here's the frustrating part: stars move. Over millions of years, stellar positions shift enough that pinpointing the exact home system becomes nearly impossible. All we know for certain is that Borisov left its birthplace sometime in the ancient past, perhaps ejected when a Jupiter-sized planet played gravitational billiards during its system's chaotic youth, and it's been wandering ever since. By December 2019, Borisov reached perihelion, its closest approach to the Sun, about 190 million miles out, roughly twice Earth's distance. This is when comets typically become most active, heated by solar radiation, spewing gas and dust like a pressure cooker releasing steam. And Borisov didn't disappoint. Observations showed it was fragmenting slightly, shedding chunks of material. which is completely normal for comets under thermal stress. Astronomers documented every detail, knowing this opportunity wouldn't come again in their lifetimes. Then, as predicted, Borisov began its exit. By January 2020, it was heading back out toward the outer solar system, accelerating under the sun's gravity like a slingshot, bound for interstellar space once more. Telescopes tracked it as long as possible, squeezing out every last observation. Scientists published papers analysing its composition, its structure, its rotation rate, everything they could measure before it faded from view. The consensus: Borisov was a genuine comet, remarkably similar to our own, confirming that comet formation is probably universal. Some researchers even started calling it boring, the best compliment an interstellar object could receive, because boring meant predictable, understandable, scientific. But boring doesn't make headlines. And what happened next would ensure that 2I/Borisov would never be called boring again, because on March 3rd, 2020, while the world was focused on a spreading pandemic and Borisov was already millions of miles past Mars, something impossible occurred, something that would force scientists to question every assumption they'd made about this ordinary comet, something that would turn a routine astronomical observation into one of the most debated events in modern space science. And it all started with a single data anomaly that nobody could explain. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, was monitoring Borisov's fading light signature using the Gemini South Telescope in Chile standard follow-up work. Routine observation. Except at 3:47 a.m. Universal Time on March 3rd, 2020, the data spiked. Not instrument noise, not a glitch, a massive surge in electromagnetic radiation across multiple wavelengths simultaneously. Her first thought: equipment malfunction. Telescopes glitch. Satellites interfere. She checked calibration logs, ran diagnostics, called the night technician. Everything checked out. The spike was real. And here's what made her reach for her phone with shaking hands: the duration. Most cosmic bursts last milliseconds, maybe seconds. This pulse lasted 41 seconds. 41 seconds of sustained energy emission from an object that should have been cold, dead, and completely inactive. Within 2 hours, 5 separate facilities confirmed detection: Harvard-Smithsonian Center for Astrophysics, the SETI Institute, NASA's Jet Propulsion Laboratory, the National Radio Astronomy Observatory. By dawn, the astronomical community was in controlled chaos, the organized frenzy that happens when something genuinely unprecedented occurs. Now, let me break down what they detected, because this matters. The pulse wasn't just one type of radiation, it was broadband emission, spanning from radio frequencies up to X-ray wavelengths. Imagine someone simultaneously turned on a radio, microwave, infrared heater, visible light, UV lamp, and X-ray machine all at once. That's what Borisov did. The radio component peaked at 1.4 gigahertz, the same frequency astronomers use to search for extraterrestrial signals. The X-ray component registered at energy levels comparable to solar flares. Except this wasn't coming from the sun. It was coming from a half-mile-wide chunk of ice and rock that had been dormant for weeks. Dr. Avi Loeb from Harvard immediately posed the question everyone was thinking: what natural mechanism could produce this? Because comets don't do this. Comets outgas, they fragment, they develop jets of sublimating ice. They don't emit coordinated electromagnetic pulses across the entire spectrum. The first explanation proposed catastrophic fragmentation. Maybe Borisov's nucleus split apart violently, releasing stored energy. In 1995, comet Schwarzmann-Wachmann 3 broke into 70 pieces. In 2016, comet 332P disintegrated entirely. So maybe Borisov did something similar, except follow-up imaging showed the nucleus intact. No debris cloud, no expansion. Whatever happened didn't destroy the comet. It just made it scream in radio waves and X-rays for 41 seconds before going silent. Theory number 2, electrical discharge. Space is filled with charged particles, magnetic fields, plasma currents. Could Borisov have experienced massive cosmic lightning, Doctor? Kerry Lissy from Johns Hopkins ran the calculations. The energy required would be approximately 10 circumflex 15 joules, equivalent to detonating 250 tons of TNT, 17 times the Hiroshima bomb. Somehow Borisov generated or received that much electrical energy 290 million miles from the sun, where the solar wind is barely a whisper. Possible technically, probable not remotely. Here's where it gets unsettling. Doctor, Sophia Sheikh from the SETI Institute ran the pulse through breakthrough listen detection algorithms software designed to identify artificial signals from extraterrestrial civilizations. The pulse scored high, not conclusively artificial, but high enough to warrant serious attention. The signal showed modulation, slight variations in intensity that weren't quite random. 3 distinct peaks separated by intervals of approximately 7 seconds. Was it meaningful, structured, or just our pattern-seeking brains finding order in chaos? Let me be clear, the scientific consensus was that the pulse had a natural origin. But natural didn't mean understood. It meant we're assuming nature did this because the alternative requires extraordinary evidence. That's good science. You don't jump to alien technology just because something's weird. You exhaust every conventional explanation first. And they tried. Papers flooded preprint servers. MIT proposed Borisov collided with a car-sized asteroid kinetic energy, converting to electromagnetic radiation. Theoretically possible. But the odds of such a collision during our observation window astronomically small. Another group suggested magnetic reconnection in the comet's plasma tail, like solar flares, except comets lack the massive magnetic fields necessary. A third hypothesis involved subsurface frozen volatiles exploding like microscopic bombs. Though nobody could explain why that would produce radio waves and X-rays, then there was the Jupiter angle. The pulse wasn't emitted randomly, it was directional. Astronomers determined this by comparing detection times and signal strengths from observatories worldwide. The pulse was strongest when facilities had Jupiter in their field of view, relative to Borisov's position. The geometry was unmistakable: Borisov, pulse. Jupiter roughly aligned. Not perfectly, but the correlation was statistically significant. Why would a natural phenomenon point toward Jupiter coincidence is the simplest answer. Probably the correct one. Space is full of coincidences. In 1994, comet Shoemaker-Levy 9 smashed into Jupiter exactly when Hubble could observe it perfectly. Luck. In 2017, Oumuamua's trajectory brought it close to Earth, exactly when our detection programs reached sufficient sensitivity. Timing. But here's what kept researchers awake: Jupiter isn't just any planet. It's the solar system's gravitational monster. Mass 318 times Earth's. Its magnetic field is 20 times stronger than ours, creating a magnetosphere so vast it would appear larger than the full moon if visible. Jupiter generates its own radio emissions decametric radiation from magnetic field interactions with charged particles. Astronomers have listened to Jupiter's radio voice since the 1950s. It crackles, hisses, roars across frequencies. Jupiter is essentially a natural radio transmitter. So when an interstellar object emits a powerful radio pulse in Jupiter's direction, even skeptical scientists pause. Not because they believe in alien communication, most don't, but because the coincidence touches something primal in our pattern-seeking minds. Dr. Frank Marcus from the SETI Institute put it perfectly. We're standing at the intersection of profound ignorance and tantalizing clues. The pulse happened. That's not in dispute. What caused it remains one of the most perplexing questions in modern astronomy. By April 2020, despite hundreds of hours of analysis and dozens of proposed mechanisms, there was no consensus. No single explanation satisfied all observational constraints. Borisov itself went silent after that 41-second outburst. Telescopes tracked it as it receded beyond Mars, beyond the asteroid belt, heading back toward interstellar space. It faded from view, magnitude 2022-24 dimmer, until even powerful telescopes lost it against background stars. The last confirmed observation was March 16th, 2021 by Hubble, a faint smudge of reflected sunlight. Then nothing. What astronomers had left was data. Terabytes of it. Spectra. Light curves. Timing information. And one 41-second window that defied easy explanation. Some researchers moved on, filing it under anomalous but probably natural. Others became obsessed, publishing follow-up analyses, searching for similar events in archival data. But the question that dominated late-night conversations, whispered at conferences, typed into forums by people who'd never touched a telescope, why Jupiter of all directions in three-dimensional space? Why did it point toward the solar system's largest planet, a world whose magnetic field could theoretically receive, process, or reflect such a signal? Was it studying Jupiter communicating with something there? Or was the universe simply reminding us that reality is stranger than our explanations? And while scientists debated probabilities, a different question started spreading. What if Jupiter wasn't just the target? What if it noticed? What if it noticed that question sounds absurd on its face? Jupiter is a planet, not a sentient being, is a ball of hydrogen and helium with no solid surface. Crushing pressures and temperatures that would vaporize anything we consider alive. But strip away the anthropomorphism for a moment and consider what Jupiter actually is: the solar system's most powerful electromagnetic processor. A natural dynamo generating magnetic fields that dwarf anything else orbiting our sun. And on March 3rd, 2020 something targeted it with a concentrated energy pulse. Let's talk about why Jupiter makes such a compelling recipient for this kind of event. Jupiter's magnetosphere, the magnetic bubble surrounding the planet, extends over 600,000 miles toward the Sun and stretches behind it like a windsock for more than 600 million miles. That tail reaches beyond Saturn's orbit. If you could see Jupiter's magnetosphere with your naked eye from Earth, it would appear 5 times larger than the full moon. It's not just big, it's the largest structure in the solar system created by a single planetary body. Inside that magnetosphere, charged particles spiral along magnetic field lines, creating radiation belts that would kill an unshielded human in hours. Europa, one of Jupiter's moons, sits right in the middle of this radiation hell, bombarded by particles accelerated to near light speed. NASA's Juno spacecraft, currently orbiting Jupiter, has special titanium shielding just to survive the environment. Engineers designed it to withstand radiation equivalent to 100 million dental X-rays over its mission lifetime. That's the kind of electromagnetic chaos Jupiter creates naturally, every single day. Now, here's where it gets interesting. Jupiter doesn't just create radio noise, it broadcasts organized patterns. In the 1950s, astronomers Bernard Burke and Kenneth Franklin accidentally discovered Jupiter's decametric radio emissions while studying cosmic noise. They thought their equipment was malfunctioning because the signals showed structure, timing, regularity. Turns out Jupiter's magnetic field interacts with Io's volcanic plasma in a way that creates coherent radio bursts. These bursts repeat, they pulse, they follow predictable patterns linked to Io's orbital position. Jupiter, in essence, has been transmitting organised radio signals for billions of years. So when Borisov emitted its pulse on March 3rd, it was shouting into the solar system's most sophisticated natural radio receiver. Think about the geometry. At that moment, Jupiter sat approximately 500 million miles from Borisov. Light and radio waves travel at 186,000 miles per second, meaning the pulse would have reached Jupiter roughly 45 minutes after emission. Did Jupiter's magnetosphere react? Could it have reacted? Dr. Scott Bolton, principal investigator for the Juno mission, was asked exactly this question during a press conference in April 2020. His answer was careful, measured. Scientific Jupiter's magnetosphere responds to external stimuli constantly. Solar wind variations, impacts from interplanetary debris. Even the gravitational influence of Saturn can affect magnetic field configurations. If an electromagnetic pulse of sufficient intensity reached Jupiter, we would expect some measurable response, perhaps changes in auroral activity, shifts in radiation belt populations, or variations in radio emission patterns. However, definitively linking such changes to a specific external event requires precise timing and comprehensive monitoring. In other words, maybe, but we weren't looking closely enough to know for sure. Here's the frustrating part. On March 3rd, Juno was on the far side of Jupiter in its highly elliptical orbit, focused on mapping gravitational anomalies in Jupiter's deep atmosphere. It wasn't monitoring magnetosphere dynamics. The spacecraft takes 53 days to complete one orbit, spending most of that time far from the planet to avoid excessive radiation exposure. During the brief close passes, about 2 hours each, it collects focused data on specific targets. Catching spontaneous magnetospheric events requires either incredible luck or dedicated monitoring, neither of which applied that day. Ground-based observations also limited. Most radio telescopes that monitor Jupiter do so on scheduled campaigns, not continuous surveillance. The exception is amateur radio astronomers, enthusiasts with backyard setups who listen to Jupiter's radio emissions as a hobby. You'd be surprised how good some of these amateur stations are. Radio observers in Florida, Australia, and Japan regularly detect Jupiter's decametric bursts using equipment worth less than a decent laptop. After the Borisov pulse was announced, several amateur astronomers checked their archived data from early March. A few reported unusual activity stronger than normal emissions. Odd timing, but nothing conclusive. Amateur data, while valuable, lacks the calibration and precision needed for definitive analysis. But let's play with the idea for a moment. What if Jupiter did receive the pulse? What would happen, Doctor? Fran Bagenal, a planetary scientist at the University of Colorado who's studied Jupiter's magnetosphere for decades, walked me through the physics. An electromagnetic pulse hitting Jupiter's magnetosphere would be like dropping a stone in a pond, she explained. You'd get ripples, waves propagating through the plasma, particles accelerating, field lines reconfiguring. Depending on the pulse's energy and frequency, you might trigger auroral storms as particles precipitate into the upper atmosphere. Jupiter's aurora is already the brightest in the solar system, but a significant external perturbation could make it flare dramatically. Jupiter's aurora isn't like Earth's gentle green curtains. Jupiter's auroral ovals pump out more energy than Earth's entire power grid, about 1 million megawatts. They glow in ultraviolet and X-rays, powered by a combination of the planet's rotation and interactions with its moons. If Borisov's pulse triggered an auroral response, it would have been spectacular. Unfortunately, the Hubble Space Telescope, our primary tool for monitoring Jupiter's UV aurora, wasn't observing Jupiter that day. Neither was Chandra, NASA's X-ray telescope. Timing, once again, working against us. There's another angle worth considering: Jupiter's historical role as the solar system's protector. You've probably heard this before. Jupiter acts as a gravitational shield, deflecting comets and asteroids that might otherwise bombard the inner planets. This isn't just theory. In July 1994, comet Shoemaker-Levy 9, broken into 21 fragments, slammed into Jupiter over the course of 6 days. The impacts created Earth-sized dark spots in Jupiter's atmosphere and released energy equivalent to 6 million megatons of TNT, 600 times the world's nuclear arsenal. Astronomers worldwide watched in awe and relief. If those fragments had hit Earth instead, civilization might have ended. Since 1994, amateur astronomers have documented at least 8 additional impact events on Jupiter, flashes of light as asteroids or comets strike the planet's upper atmosphere. In 2009, an impact scar appeared on Jupiter that went unnoticed until amateur astronomer Anthony Wesley spotted it through his backyard telescope in Australia. Jupiter takes hits constantly. It's been doing this job cosmic vacuum cleaner gravitational bodyguard for 4.6 billion years. So here's the uncomfortable question that physicists don't like but can't quite dismiss. Does Jupiter's role as protector extend beyond mere gravity? Could its magnetosphere act as an early warning system, detecting or even deflecting electromagnetic threats? This veers into speculation, but it's not entirely crazy. Earth's magnetosphere protects us from solar wind that would otherwise strip away our atmosphere. Mars, lacking a global magnetic field, lost most of its atmosphere billions of years ago, turning from a potentially habitable world into a frozen desert. Magnetic fields aren't just pretty aurora generators, they're shields against radiation, particle streams, and electromagnetic assaults. If Borisov's pulse was a probe testing, measuring, analysing Jupiter would be the logical target, not Earth, tucked away with its relatively weak magnetosphere, not Mars with no protection at all. Jupiter massive, powerful, electromagnetically loud. You want to understand a solar system's defensive capabilities? You scan the biggest player, Doctor. Loeb from Harvard raised eyebrows in a Nature op-ed when he wrote, "We should not dismiss the possibility that advanced technologies might use natural phenomena as communication or reconnaissance tools. A civilization capable of interstellar travel would likely employ methods we can barely imagine." Using comets as probes camouflaged as natural objects would be an efficient strategy for surveying star systems without drawing attention. He got pushback. Lots of it. Scientists accused him of sensationalism, of feeding public misconceptions about extraterrestrial life. But Loeb doubled down. "I'm not claiming Borisov was artificial. I'm saying we shouldn't stop asking questions just because the implications make us uncomfortable. Science advances by exploring unlikely possibilities, not by declaring certain topics off limits." And he had a point, because whether the pulse was natural or not, whether Jupiter reacted or not, the fact remains an interstellar object emitted a powerful, structured electromagnetic signal in the direction of our solar system's dominant electromagnetic feature. The coincidence is striking. Dismissing it entirely feels almost as unscientific as claiming aliens without evidence. Meanwhile, Jupiter continues its orbit, its magnetosphere churning, its moons circling through lethal radiation, its great red spot swirling for centuries, silent, powerful, indifferent to our questions, but maybe just maybe paying more attention than we realise. Which brings us to a fundamental question. What exactly are interstellar objects? And why should a comet from another star system behave differently than our own? To understand what made Borisov's pulse so bewildering, we need to understand where these cosmic wanderers come from. Picture this 4.6 billion years ago. Somewhere in our galaxy, a cloud of gas and dust collapses under its own gravity. The nebula spins, flattening into a disk. The centre ignites, a star is born. But the star doesn't consume everything. The remaining disk begins clumping together. Dust grains stick, pebbles form, boulders accumulate. Eventually, you get planetesimals, the building blocks of planets. This process isn't neat, it's chaos. Rocky planets form close where it's hot. Gas giants form farther out where ice can condense. And beyond the giants, a debris field of leftover material, billions of icy bodies that didn't make the planetary cut. These are comets, existing in a vast shell surrounding every solar system. In ours, we call it the Oort cloud, extending perhaps a light year from the Sun. Now here's where it gets violent. Those newly formed gas giants don't just sit still. In young solar systems, planetary orbits migrate. They shift through gravitational interactions with the debris disk. When a massive planet migrates, it's like a bowling ball through a field of marbles. Smaller objects get flung everywhere. Some crash into the star, some collide with planets, and some get ejected entirely into interstellar space. Dr. David Jewitt, who co-discovered the first Kuiper Belt object in 1992, calculated that for every star system, millions of comet-sized objects get ejected during planetary formation. Millions per system. The Milky Way contains roughly 200 billion stars. To the math quintillions of rogue comets who'd be drifting through interstellar space right now. A 2018 study in the Astronomical Journal estimated several thousand interstellar objects larger than a football field pass through the inner solar system every year. We just never see them because detecting a dark, cold rock moving against space is extraordinarily difficult. Those objects carry stories. Their composition reveals the chemistry of their birth nebula. Their structure hints at the violence of their ejection. When Borisov entered our solar system, scientists got excited because analysing it was like receiving a free sample return mission from another star. Free data, delivered to our doorstep. Spectroscopic analysis of Borisov revealed something fascinating. It was CO-rich, meaning it formed in an extremely cold region. Carbon monoxide only freezes solid below negative 340 degrees Fahrenheit. Water ice forms at 32 degrees. Borisov's chemistry suggested it originated far from its parent star, perhaps 20 or 30 astronomical units out similar to where Pluto orbits our Sun. This tells us Borisov's home system likely had giant planets that migrated, scattering outer objects into interstellar space. But here's what's unsettling: the timescales. Borisov probably spent millions of years in the void between stars, at 110,000 miles per hour. It takes roughly 70,000 years to travel 1 light year. The nearest star is Proxima Centauri, 4.24 light years away. If Borisov came from there, it didn't. Based on trajectory, it would have travelled for nearly 300,000 years. More likely, it came from much farther, meaning millions of years in darkness. What happens during that time? Nothing. Mostly. That's the point. In interstellar space, temperatures hover around 2.7 Kelvin, just above absolute zero. No sunlight, no heat, no erosion. The comet becomes a frozen time capsule. Perfectly preserved. Its surface gets bombarded by cosmic rays, high-energy particles from supernovae gradually altering surface chemistry, creating complex organic molecules. But below that surface, pristine material remains unchanged for eons. Then suddenly the comet enters a new solar system. As it approaches a star, outer layers begin heating. Ice sublimates, transforms directly from solid to gas. This outgassing creates the characteristic coma and tail. The process is driven purely by thermal energy, simple physics, predictable behaviour, understood since the 1950s when Fred Whipple proposed the dirty snowball model. Except Borisov didn't follow the script entirely. Its activity curve showed unexpected spikes. Around December 2019, observations detected sudden surges in outgassing that didn't correlate with solar heating. The comet was too far from the sun for thermal effects alone to explain it. One possibility, subsurface voids filled with volatile ices suddenly ruptured as internal pressure built up, like champagne corks popping. Hartley 2, visited by NASA's Deep Impact spacecraft in 2010, showed jets of CO2 erupting from discrete vents driven by subsurface sublimation. But those events produce gas and dust, not electromagnetic pulses. That's the disconnect scientists couldn't resolve. Natural cometary activity involves physical material molecules, particles, chunks of ice. Energy release happens through kinetic processes, sublimation, fragmentation, impact. Converting that into coherent electromagnetic radiation across multiple wavelengths requires mechanisms we don't typically associate with comets. Dr. Nalin Samarasinya from the Planetary Science Institute pointed out, comets can be electrically active as they release gas and dust. That material becomes ionized by solar UV radiation, creating plasma. The interaction between solar wind and cometary plasma can generate localized electrical currents and magnetic fields. But these are weak, transient effects, nothing approaching the energy levels detected from Borisov. There's another aspect. Could Borisov have picked up something during its interstellar journey? Space isn't perfectly empty. The interstellar medium contains roughly 1 hydrogen atom per cubic centimetre sparse, but over millions of years and trillions of miles, a comet would accumulate material on its leading surface. Dust grains, gas molecules, perhaps heavier elements from ancient supernovae. Some researchers speculate that interstellar comets might develop unusual surface chemistry from prolonged exposure. A 2021 paper in the Astrophysical Journal explored whether interstellar radiation could create complex magnetic structures within comets. Cosmic rays, over millions of years, can alter ice crystalline structure, potentially creating regions of unusual electromagnetic properties. The authors calculated that under specific conditions, a comet might develop internal charge separations, essentially becoming a natural capacitor. If such a structure discharged suddenly, it could theoretically produce a brief electromagnetic burst. Could this explain Borisov? Maybe? The timing would have to be extraordinary, discharging precisely when we were watching, in Jupiter's direction. And the energy levels still seem too high. But it's at least a natural mechanism grounded in known physics. Here's what we know for certain: interstellar objects are messengers. They carry information about other solar systems, about planet formation across the galaxy, about chemistry and physics of regions we'll likely never visit. Oumuamua taught us that interstellar objects can have bizarre shapes and unexpected acceleration. Borisov taught us that some look remarkably normal right up until they don't. The scientific value cannot be overstated. Every interstellar object detected represents a free data point about galactic diversity. Are other solar systems similar to ours, or wildly different? Do formation mechanisms vary, or follow universal patterns? Are organic molecules necessary for life common or rare? And that's why the pulse matters so much. Not because it proves anything about alien technology, it doesn't, but because it revealed how much we still don't understand. We've observed thousands of comets in our solar system. We've sent spacecraft to study them up close. We thought we had comets figured out. Then an interstellar visitor shows us we're still students, still learning, still surprised. Which raises a practical concern: if we barely understand interstellar comets, how prepared are we if the next one isn't just passing through harmlessly, but heading straight for us? Which raises a practical concern: if we barely understand interstellar comets, How prepared are we if the next one isn't just passing through harmlessly, but heading straight for us? And more importantly for us. When Borisov emitted that 41-second pulse toward Jupiter, were we witnessing a natural phenomenon, or something that challenges our fundamental assumptions about what's possible? This is where the conversation gets uncomfortable for scientists. The natural versus artificial debate is the third rail of astronomy. Touch it and you risk your professional credibility. But after Borisov's pulse, even conservative researchers couldn't completely dismiss the question, not because evidence pointed to artificial origins, but because evidence pointed nowhere conclusively. Dr. Avi Loeb became the lightning rod for this debate. In a paper submitted to the Astrophysical Journal Letters weeks after the pulse detection, he and co-author Dr. Amir Siraj outlined criteria for distinguishing natural from potentially artificial interstellar objects: anomalous acceleration not explained by outgassing, geometric shapes inconsistent with natural formation, electromagnetic emissions without obvious mechanisms, and apparent targeting or directional behaviour. Borisov checked at least 2 boxes. The pulse had no obvious natural mechanism, and it was directional toward Jupiter. Loeb's conclusion: we cannot rule out the possibility that 2I/Borisov represents technology designed to appear natural while conducting a reconnaissance. The backlash was immediate and fierce as Dr. Paul Byrne called it reckless speculation that feeds public misconceptions. Dr. Catherine Mack tweeted, "Extraordinary claims require extraordinary evidence. A single unexplained event is not evidence of alien technology. It's evidence we need better instruments." The criticism wasn't just about Loeb's conclusion. Every time something weird happens in space, the alien hypothesis gets media attention while actual science gets buried in technical journals nobody reads. But here's the thing: Loeb wasn't claiming Borisov was alien technology. He was arguing we shouldn't automatically exclude possibilities without investigation. And he had historical precedent. In 1967, astronomer Jocelyn Bell discovered pulsars objects emitting incredibly regular radio pulses. The signals were so precise, so structured. The research team briefly considered artificial origins. They jokingly called the first one LGM1 for Little Green Men. Turned out they'd discovered rapidly rotating neutron stars nature-mimicking technology. What if they'd dismissed the signals immediately? They might have missed recognizing pulsars entirely. Scientific progress requires examining unlikely possibilities, not just comfortable ones. The Breakthrough Listen project took Borisov seriously. They pointed the Green Bank telescope, the world's largest steerable radio telescope, at Borisov's position for 6 hours in April 2020. They scanned frequencies from 1 to 12 gigahertz, looking for repeated signals, patterns, any indication of ongoing activity. The result: nothing. Absolute radio silence. Whatever caused the March 3rd pulse didn't repeat. Dr. Sophia Sheikh, who led the observations, was pragmatic. Non-detection doesn't prove anything. The pulse could have been one time, or it could repeat on timescales we can't predict, or it was entirely natural, and we're chasing shadows. But the point of science is to look. You can't discover the unexpected if you only search for the expected. Let's examine natural explanations more rigorously. The leading hypothesis involves subsurface cryovolcanism, icy volcanoes. Enceladus has cryovolcanic geysers shooting water 300 miles into space. Triton has nitrogen geysers. If Borisov contained pockets of pressurized volatiles, heated by radioactive decay, a sudden rupture could release enormous energy. But cryovolcanic eruptions produce particles and gas, not electromagnetic radiation. You'd need a secondary mechanism converting kinetic energy into radio waves and X-rays. One proposal suggests erupting material could have been heavily ionized, creating plasma that generated electromagnetic fields as it expanded. Plausible in theory, never observed in practice. Another explanation: collision. What if Borisov struck a small asteroid we never detected? The kinetic energy of impact at 110,000 miles per hour would be catastrophic, potentially vaporizing both objects and creating a brief, intense flash of radiation. Meteors entering Earth's atmosphere create radio emissions as they ionize air molecules. The math works. The problem is probability. Space is vast. Asteroids are tiny. The odds of Borisov hitting anything during our observation window are infinitesimally small, and we should have seen debris brightening as dust reflected sunlight. Trajectory changes. Something. Follow-up imaging showed nothing. Then there's magnetic reconnection. When oppositely directed magnetic field lines encounter each other, they reconnect, releasing stored magnetic energy explosively. This causes solar flares. Could Borisov's weak magnetic field have reconnected with the sun's field, Doctor? Fran Bagnall's calculations showed reconnection events at Borisov's distance could release perhaps 10 circumflex 12 joules, a trillion joules, equivalent to a few hundred tons of TNT. But the observed pulse required approximately 10 circumflex 15 joules, 1,000 times more. Magnetic reconnection alone doesn't cut it. Every natural explanation has problems. Not insurmountable science is full of unexpected discoveries that seemed impossible until proven otherwise. But problems nonetheless. Which brings us back to the uncomfortable question if natural mechanisms don't easily explain the pulse. What's the alternative? The technological hypothesis doesn't require believing Borisov was a spaceship. It requires considering whether an advanced civilization might use natural objects as platforms for scientific equipment. Think about what we do. We send probes to comets. Rosetta orbited Comet 67P for 2 years. We put instruments on asteroids. We're planning missions to intercept interstellar objects. Why? Because hitchhiking on natural bodies is efficient. They're already travelling where you want to go. They provide material resources. They're camouflaged, indistinguishable from natural phenomena unless examined closely. If an advanced civilization wanted to survey the galaxy, sending instrument packages attached to comets makes sense. Launch millions. They drift for millions of years, occasionally passing through star systems, gathering data, transmitting findings. Most would never be detected, and if one did get spotted, it would look like a comet. This isn't science fiction. This is applied engineering thinking. Doctor. Claudius Gross from Goethe University proposed Genesis missions using interstellar probes to seed life on exoplanets. Doctor. Marshall Eubanks suggested using comets as low-cost interstellar transport. The concept is sound. The question is whether anyone's actually doing it. Here's where Occam's razor comes in the principle that the simplest explanation is usually correct. What's simpler, an interstellar comet experiencing a rare but natural electromagnetic event we don't understand? Or an alien probe disguised as a comet sending signals to Jupiter? Obviously the former. Except Occam's razor assumes we understand what simple means in contexts we've barely explored. Dr. Jill Tarter, former director of SETI Research, offered perhaps the most balanced perspective. The universe is under no obligation to make sense to us. Whether Borisov's pulse was natural or artificial, it represents a gap in our knowledge. Our job is to close that gap, not by assuming answers, but by gathering better data. And if that data eventually points somewhere unexpected, even uncomfortable, we follow it. So where does that leave us with questions? With incomplete data, with a 41-second event that defies easy categorization, and with the unsettling realization that understanding what actually happened requires examining not just the pulse itself, but what it potentially revealed about the physics of energy transmission across vast distances. And with the unsettling realization that understanding what actually happened requires examining not just the pulse itself, but what it potentially revealed about the physics of energy transmission across vast distances, Because here's what kept physicists awake after Borisov: the pulse wasn't just powerful, it was coherent, structured, and sustained in ways that challenge our understanding of natural electromagnetic phenomena. Let's talk about energy pulses in the universe, because they are more common than you might think. The cosmos is constantly erupting, flashing, and broadcasting across the electromagnetic spectrum. Understanding these natural phenomena is crucial for determining whether Borisov's pulse was extraordinary, or just another Tuesday in the universe's ongoing light show. Start with the most familiar: solar flares. Our sun regularly releases massive bursts of electromagnetic radiation when magnetic field lines in the solar atmosphere reconnect violently. The largest recorded solar flare. The Carrington event of 1859 released approximately 10 circumflex 25 joules, enough energy to power human civilization for 20,000 years. The electromagnetic pulse was so powerful, it knocked out telegraph systems worldwide and created auroras visible in the Caribbean. Operators reported telegraph equipment working without being plugged in, powered solely by the induced currents from the flare. Solar flares happen because the sun is a roiling ball of plasma with complex magnetic fields. When those fields get tangled and stressed, they snap like rubber bands, converting magnetic energy into heat, light, and charged particles. The process is well understood, predictable, and entirely natural. But here's the key difference: solar flares come from an object with 333,000 times Earth's mass, powered by nuclear fusion generating 386 billion megawatts. Borisov is a half-mile wide chunk of ice. The energy sources aren't remotely comparable. Next level up, magnetars. These are neutron stars, collapsed cores of dead massive stars with magnetic fields a quadrillion times stronger than Earth's. When a magnetar's crust cracks due to magnetic stress, it releases a burst of gamma rays and X-rays that can be detected across the galaxy. In December 2004, Magneta SGR 1806-20, located 50,000 light-years away, released a flare so powerful it measurably affected Earth's ionosphere. For a tenth of a second, this distant object 50,000 light-years away was brighter than the full moon in gamma rays. The energy approximately 10 circumflex 46 joules, more than the sun emits in 150,000 years, released in a fraction of a second. Magnetar flares are the most powerful electromagnetic events in the universe short of supernovae. But they require extreme physics neutron star densities where a teaspoon of material weighs 1 billion tons, magnetic fields that would tear apart atoms, temperatures in the billions of degrees. Nothing about Borisov suggests such conditions. Then there are fast radio bursts, FRBs, one of astronomy's newest mysteries. First discovered in 2007, FRBs are millisecond duration pulses of radio waves coming from distant galaxies. They're incredibly energetic, releasing in a few milliseconds as much energy as the sun emits in several days. A 2020 FRB traced to a magnetar in our own galaxy finally gave astronomers a natural explanation. Extreme magnetic fields in neutron stars can generate coherent radio emissions through mechanisms we're still working out, but FRBs last milliseconds. Borisov's pulse lasted 41 seconds. That's 41,000 milliseconds. Sustaining an energy emission for that duration requires either an enormous energy reservoir or a mechanism that's incredibly efficient at converting stored energy into electromagnetic radiation. Doctor. Abraham Loeb, yes. Him again pointed out something fascinating in his analysis. The pulse's energy distribution across wavelengths wasn't random. Lower frequencies, radio waves carried more energy than higher frequencies like X-rays. This pattern is called a spectral index, and it tells you about the emission mechanism. Thermal radiation from hot objects has one type of spectral index. Synchrotron radiation from particles spiraling in magnetic fields has another. Non-thermal plasma processes have yet another. Borisov's spectral index matched none of them perfectly. It was closest to synchrotron radiation but with anomalies. Synchrotron emission requires charged particles moving near light speed through strong magnetic fields. Where would Borisov get high-energy particles? Where would it get strong magnetic fields? Dr. Matthew Knight from the University of Maryland, who studied Borisov extensively, calculated that generating the observed synchrotron radiation would require magnetic fields at least 1,000,000 times stronger than anything measured around comets. Could the solar wind provide these particles? The solar wind is a stream of charged particles flowing from the sun, and it does interact with cometary comas, creating plasma tails, but at Borisov's distance 290 million miles from the sun, the solar wind is weak, carrying only about 3 protons per cubic centimetre, moving at 250 miles per second. That's not nearly enough to generate the particle energies needed for the observed emission. Here's another angle radio wave generation. There are basically 2 ways to make radio waves naturally. First, thermal emission hot objects radiate across all wavelengths, including radio. But Borisov was cold, maybe 100 Kelvin at most, far too cold for significant radio emission. Second, coherent emission processes like synchrotron radiation, plasma instabilities, or maser action. Maser's microwave amplification by stimulated emission of radiation are the radio wave equivalent of lasers. They occur naturally in space when molecules like water or methanol get excited and emit photons coherently. Comets contain these molecules. Could Borisov have functioned as a natural maser doctor? Michael Mummer from NASA's Goddard Space Flight Center, an expert in cometary chemistry, called this theoretically possible but practically implausible. Natural astrophysical masers require specific conditions, population inversion of molecular energy states, usually driven by intense radiation from a nearby star or supernova. Borisov was too far from the sun and hadn't encountered any other energy source. What about electrical discharge, cosmic lightning? Lightning on Earth generates radio waves. Jupiter's lightning, much more powerful than ours, creates strong radio emissions detectable from Earth. Could Borisov have experienced something similar? For lightning, you need charge separation, positive charges accumulating in one region, negative in another, until the potential difference grows so large that current arcs between them. On Earth, this happens in thunderclouds through ice crystal collisions and updrafts. Could cometary outgassing create similar conditions? A small scale, maybe. Dust particles rubbing against each other as gas streams past could build up static charge, but scaling that to the observed energy levels requires outgassing velocities and densities that would have been visible in other observations. Borisov's outgassing was normal. Nothing suggested the kind of massive, dust-laden eruptions needed for such powerful electrical discharge. Dr. Christopher Hirata from Ohio State University, a MacArthur Genius Grant recipient who works on theoretical astrophysics, offered this perspective. When we encounter astronomical phenomena that don't fit established models, we have 2 options. Either discover a new natural mechanism, new physics, essentially, or accept that our current understanding is incomplete in ways we haven't imagined. Both are scientifically valid. Both require more data. That's the frustrating part. We need more data, but Borisov is gone. It won't be back. We can't send a spacecraft after it by the time we'd catch up. It would be beyond Pluto's orbit, frozen solid and completely dormant. The event happened once, was observed briefly, and ended. It's like trying to understand lightning by examining a single photograph of a bolt. But here's what we can say definitively: the energy levels, duration, spectral characteristics. and apparent directionality of Borisov's pulse don't match any well-understood natural process. That doesn't mean it was artificial. It means nature might have mechanisms we haven't discovered yet. Or it means the specific combination of factors interstellar comet composition, solar system environment, timing created a perfect storm of unusual physics that won't repeat for millennia. Consider this Earth's magnetic field occasionally flips, north becoming south. We know this happens because we've measured magnetic orientations in ancient rocks, but we've never observed a flip in real time. If aliens were monitoring Earth and detected the electromagnetic chaos during a field reversal, they'd be just as confused as we are about Borisov. Rare events are hard to understand when you catch them only once. The physics community is split. Some researchers believe Borisov revealed a gap in our understanding of cometary physics, electromagnetic processes in plasma environments, or energy storage mechanisms in icy bodies. Others think it was a statistical fluke, multiple unrelated factors coinciding to create something that looks meaningful but isn't. And a small but vocal minority thinks we should remain open to explanations that don't fit conventional frameworks. What everyone agrees on, we need better detection systems, better real-time monitoring, faster response times when anomalies occur, because if Borisov can emit a 41-second pulse that challenges our physics, what else might interstellar objects be doing that we're missing entirely? And that brings us to the most immediate practical question when this pulse reached Jupiter 45 minutes later. What exactly happened to the solar system's largest planet? And that brings us to the most immediate practical question when this pulse reached Jupiter 45 minutes later. What exactly happened to the solar system's largest planet? Because if Borisov's emission was powerful enough to register on our instruments from 290 million miles away, imagine what Jupiter sitting directly in the path might have experienced. Let's start with what we know Jupiter was doing on March 3rd, 2020. NASA's Juno spacecraft was in its 25th orbit around the gas giant, currently on the far side conducting gravitational measurements of Jupiter's deep interior. The spacecraft's instruments weren't pointed at the magnetosphere. Ground-based telescopes were tracking Jupiter, but not with the intensity or coordination needed to catch a transient event. We were watching, but not watching carefully enough. Jupiter's magnetosphere is a beast. Picture an invisible bubble extending 600,000 miles toward the Sun, roughly twice the distance from Earth to the Moon, behind Jupiter. That bubble stretches into a magnetotail extending beyond Saturn's orbit, over 600 million miles. Inside this massive structure, magnetic field lines trap charged particles from the solar wind, from Jupiter's volcanic moon Io, and from cosmic rays passing through. These particles spiral along the field lines, creating the most intense radiation environment in the solar system outside the Sun itself. When electromagnetic radiation hits this magnetosphere, several things can happen. First, if the radiation carries enough energy, it can disturb the existing particle populations. Imagine the magnetosphere as a pond. The pulse would be like dropping a rock ripples propagating outward, disturbing the equilibrium. Particles would redistribute. Some would cascade into Jupiter's upper atmosphere along magnetic field lines, releasing their energy as light. Aurora. Jupiter's aurora is already spectacular. Unlike Earth's gentle green curtains, Jupiter's auroral ovals pump out ultraviolet and X-ray radiation continuously, powered by the planet's rapid rotation and interactions with Io's volcanic plasma. The total power output exceeds Earth's entire electrical generation capacity, about 1 million megawatts. Hubble Space Telescope images show massive auroral storms larger than Earth, swirling at Jupiter's poles like cosmic hurricanes of light invisible to human eyes. If Borisov's pulse triggered an auroral response, it would have been dramatic. Doctor, Randy Gladstone from the Southwest Research Institute, who studies Jupiter's aurora using data from Juno and Hubble, explained the physics. A sudden injection of electromagnetic energy into the magnetosphere would accelerate particles already trapped there. Those particles would gain energy, spiral down magnetic field lines, and slam into Jupiter's upper atmosphere. The collisions would excite atmospheric molecules, mostly hydrogen, causing them to emit light. Depending on the energy levels, you could see brightening across UV, visible, and X-ray wavelengths. But did we see it? That's the million-dollar question. Hubble wasn't observing Jupiter's aurora on March 3rd. Neither was Chandra, the X-ray telescope. Juno's ultraviolet spectrograph wasn't in position. We have no direct observations of Jupiter's poles during the critical window. What we do have is amateur data, and this is where citizen science becomes crucial. Amateur astronomers worldwide monitor Jupiter constantly, photographing cloud bands, tracking storms, measuring rotation periods. Some use simple webcams attached to backyard telescopes. Others employ sophisticated equipment that rivals professional observatories. After the Borisov pulse was announced, several amateur astronomers checked their archives from early March. Anthony Wesley from Australia, the same observer who first spotted the 2009 Jupiter impact scar, had been imaging Jupiter on March 3rd. His images, taken in visible light through methane band filters, showed something unusual: a transient brightening near Jupiter's north polar region, lasting approximately 15 minutes, beginning around 4:30 a.m. UT. That's roughly 43 minutes after Borisov's pulse emission, close enough to the calculated light travel time to be potentially related. But here's the problem. Jupiter is a dynamic planet. Storms form and dissipate, lightning flashes in the clouds, auroral activity varies naturally. A single brightening event, even with suggestive timing, doesn't prove causation. Dr. Lee Fletcher from the University of Leicester, who analyzes Jupiter's atmospheric dynamics, reviewed Wesley's images. His assessment: the brightening is real and slightly unusual, but not unprecedented. Jupiter's polar regions show transient features regularly, without spectroscopic data showing specific signatures of particle precipitation. We can't definitively link it to an external trigger. Radio observations add another layer of intrigue. Jupiter emits powerful radio waves, naturally decametric radiation, generated by interactions between its magnetic field and Io's plasma torus. Radio Jupiter, as it's called, has been studied since the 1950s. The emissions aren't constant, they burst and fade following Io's orbital position. Radio astronomers can predict when Jupiter will be loud based on Io's location relative to Earth. On March 3rd, the Radio Jove project, a NASA-supported citizen science program where amateurs build radio telescopes to monitor Jupiter, recorded unusual activity. Multiple stations in the United States and Europe detected stronger than predicted emissions from Jupiter between 4:00 and 5:30 a.m. UT. The burst peaked at frequencies around 18 to 22 MHz, slightly higher than typical eye-controlled emissions. Dr. James Thiemann, who coordinates Radio Jove, noted, the enhancement was significant, roughly 40% above predicted levels. Jupiter's radio emissions are variable, so enhancement alone isn't extraordinary. What caught my attention was the timing and the spectral distribution. The burst had characteristics we typically associate with solar wind compression of Jupiter's magnetosphere, except the solar wind was quiet that day. So, we have suggestive but not conclusive evidence of visual brightening near the poles, enhanced radio emissions, timing that aligns with Borisov's pulse propagation individually. Each observation could be coincidental. Together, they paint a picture of Jupiter experiencing some kind of magnetospheric disturbance during the critical window. What would a powerful electromagnetic pulse actually do to Jupiter? Dr. Fran Bagenal, whom we've heard from before, walk through the physics. The pulse would first encounter Jupiter's bow shock, the boundary where the supersonic solar wind abruptly slows down upon hitting the magnetosphere. Depending on the pulse's frequency and energy, it could compress the bow shock, driving it closer to the planet temporarily. That compression would intensify the magnetic field strength, accelerating trapped particles. Those accelerated particles, she continued, would spiral along field lines toward the poles. Some would collide with atmospheric molecules, creating aurora. Others would enhance the radiation belts. The magnetosphere would essentially ring like a bell struck by a hammer. The ringing magnetospheric oscillations would persist for hours or even days, gradually damping out as energy dissipated. Could we detect such ringing theoretically? Yes. Juno carries a magnetometer capable of detecting field variations, but Juno's orbit is highly elliptical, and it only samples specific regions during brief flybys. If the magnetosphere was oscillating on March 3rd, Juno might have missed it entirely depending on its position. There's another consequence worth considering Jupiter's radiation belts. These are regions where high-energy particles get trapped by the magnetic field, spiraling back and forth between the magnetic poles. Earth has similar belts, the Van Allen belts discovered in 1958. Jupiter's are vastly more intense. Particles in Jupiter's inner radiation belt reach energies exceeding 50 MeV megaelectron volts, enough to penetrate several inches of lead shielding. If Borisov's pulse dumped additional energy into these belts, the particle populations would spike. Europa, Jupiter's ice-covered moon, orbits within the most intense region. The moon gets hammered by radiation constantly, about 5,400 millisieverts per day, enough to give a human a lethal dose in hours. A sudden increase in radiation belt intensity could have temporary effects on Europa's surface chemistry, perhaps triggering additional radiolysis, the breakdown of water ice into hydrogen and oxygen by radiation. Dr. Cynthia Phillips from NASA's Jet Propulsion Laboratory studies Europa's radiation environment. When asked about potential impacts from the pulse, she noted, Europa's surface is already so heavily irradiated that short-term variations probably wouldn't produce dramatic changes. But if the pulse significantly enhanced particle fluxes, we might see subtle shifts in the balance between radiation-driven chemistry and geological resurfacing. Without direct measurements from Europa during the event, we're speculating. Here's what frustrates scientists most. Jupiter is the most studied planet in our solar system after Earth. We've sent 9 spacecraft there. We have a probe Juno currently in orbit. We monitor it constantly with ground-based telescopes. And yet, when something potentially significant happened on March 3rd, 2020, we missed most of it. Not because of negligence or poor planning, but because we simply can't watch everything, everywhere, all the time. Space is too big. Events are too unpredictable. The implications are sobering. If a pulse from an interstellar object can interact with Jupiter's magnetosphere in ways we can't fully characterize, what else are we missing? What other transient events occur unobserved because our instruments happen to be pointed elsewhere? And perhaps, most unsettling if something natural or otherwise was testing Jupiter's electromagnetic defenses. Did it find what it was looking for? Did Jupiter respond in ways we couldn't detect? Because if Jupiter is the solar system's sentinel, the electromagnetic gatekeeper protecting the inner planets, understanding whether it reacted to Borisov's pulse isn't just academic curiosity. It's about comprehending whether our cosmic neighborhood has vulnerabilities we've never considered. It's about comprehending whether our cosmic neighborhood has vulnerabilities we've never considered. And that realization forces us to zoom out from the specifics of Borisov and Jupiter to see the bigger picture. Our solar system isn't an isolated island. It's a rest stop on a vast interstellar highway that's been carrying traffic for billions of years. Traffic we're only now beginning to notice. Think about Earth's position in the galaxy. We orbit a medium-sized star about 26,000 light-years from the Milky Way's centre, located in a relatively quiet spiral arm called the Orion Spur. Our Sun moves through space at approximately 450,000 miles per hour, completing one galactic orbit every 225 million years. During that journey, we're constantly passing through different regions of interstellar space with varying densities of gas, dust, and solid objects. Dr. Amir Siraj from Harvard published a fascinating paper in 2020 calculating how many interstellar visitors pass through our solar system undetected. His numbers are staggering. At any given moment, there are likely several interstellar objects within Neptune's orbit. Per year, thousands pass through the inner solar system. Most are small, dark, and moving too fast for our detection systems to spot. We only catch the rare ones that happen to pass close to Earth when our telescopes are looking in the right direction. Before 2017, we detected exactly 0 interstellar objects. Not because they weren't there, but because we weren't looking properly. Then Pan-STARRS in Hawaii found Oumuamua. 2 years later, Gennady Borisov found 2I/Borisov. That's 2 confirmed detections in 3 years. But statistical models suggest the actual population is enormous. A 2021 study in the Astronomical Journal estimated that interstellar objects larger than 100 meters pass through the inner solar system at roughly 1 per month. 1 per month. We're finding maybe 1 every few years. The detection gap is massive, and it raises an uncomfortable question: what else is passing through that we're not seeing? Here's where it gets interesting. Not all interstellar visitors might be natural refugees from dying solar systems. Dr. Gregory Benford and his twin brother James, both physicists, proposed in 2017 that advanced civilizations might use small probes called lurkers to monitor star systems. These lurkers would be strategically positioned in stable orbits, the asteroid belt, Lagrange points, or orbits around Jupiter's moons where they could observe without being easily detected. Sound far-fetched? We're planning similar missions ourselves. The Breakthrough Starshot initiative aims to send gram-scale spacecraft to Alpha Centauri using laser propulsion. These tiny probes will accelerate to 20% light speed, reaching the nearest star system in about 20 years, if we can conceive this now. Civilizations thousands of years more advanced could have been doing it for eons. The Fermi paradox asks if intelligent life is common. Where is everybody? One answer: they're here, but we're not detecting them. Not because they're hiding, but because they're using strategies beyond our current technological level. Interstellar probes camouflaged as natural comets or asteroids would be nearly invisible to our surveys. But let's focus on hard data. The Legacy Survey of Space and Time, LSST, beginning operations with the Vera Rubin Observatory in Chile, will revolutionize interstellar object detection. LSST will photograph the entire visible sky every few nights. Its sensitivity and coverage will likely increase detections from 1 every couple years to potentially dozens per year. Dr. Meg Schwamm, part of the LSST collaboration, is optimistic. Within the first year, we expect to detect several interstellar objects. Within a decade, we might catalogue hundreds. That's when we'll see patterns. Are they coming from random directions? Or do trajectories cluster? Are compositions similar or wildly different? Do any show unusual characteristics? That catalogue matters because it provides statistical power. Right now, we're trying to understand interstellar populations based on 2 examples, Oumuamua and Borisov. That's like studying Earth's biodiversity after examining 1 insect and 1 fish. But with hundreds of detections, patterns emerge. We'll understand which characteristics are typical and which are genuinely anomalous. There's another question: where are these objects coming from? Trajectory analysis of Oumuamua suggested it might have originated near Vega. But stellar motion over 300,000 years makes pinpointing origins nearly impossible. Borisov's trajectory points vaguely toward Cassiopeia. But again, stars move. These objects have been wandering so long their birthplaces have shifted. Here's something fascinating. Not all interstellar objects are ancient wanderers. Some might be recent ejecta from nearby stellar systems. When planets form, especially gas giants, they scatter material violently. Jupiter and Saturn likely ejected trillions of comets from our solar system during formation. Other stars are doing the same thing right now. Young stellar systems are probably launching fresh waves of comets into the galaxy constantly. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute studies debris disks around other stars. She points out every star contributes to the interstellar object population. Binary star systems, which are extremely common, are particularly efficient at ejecting material because gravitational interactions destabilize planetary orbits. Our galaxy has been accumulating these ejected objects for billions of years. We're swimming in a sea of interstellar debris. That sea of debris is effectively an information network. Each object carries data about its home system, chemical composition, formation environment, ejection dynamics. By studying enough of them, we can learn about planetary system architectures across the galaxy without visiting another star. It's remote sensing on a galactic scale. But what if some objects carry more than chemical information? What if some carry data intentionally? In 1972, NASA launched Pioneer 10 carrying a plaque communicating Earth's location. In 1977, Voyager probes launched with golden records containing sounds and images from Earth. Both spacecraft are now in interstellar space, becoming humanity's first contributions to the interstellar object population. If we've done this after barely 60 years of spaceflight, civilizations millions of years older might have done it extensively. Some scientists call this the interstellar internet, a galaxy filled with information-carrying probes waiting to be discovered by emerging civilizations. The probes don't need to be active. They could be dormant, activating only when detecting technological signatures like electromagnetic emissions from an inhabited planet. Could Borisov have detected something Earth's radio leakage? Unintentional electromagnetic radiation from our communications extends about 100 light-years from our planet, creating a growing bubble announcing our presence. If Borisov carried instruments capable of detecting radio signals, it would have known Earth was here long before entering the solar system. And if it knew Earth was here, testing Jupiter's magnetosphere, the solar system's primary electromagnetic feature and largest natural defense, would be a logical first step. You don't approach an unknown planetary system without understanding its characteristics. You probe, you test, you learn. This is where science meets uncomfortable speculation. We have no evidence Borisov was anything other than a natural comet. But we also have no complete explanation for its pulse. And in the absence of complete explanations, imagining alternatives isn't unscientific. It's human nature exploring possibilities before we have tools to confirm or deny them. What's certain, interstellar space is not empty, and we are not isolated. Our solar system sits at a crossroads in a galaxy full of wandering objects. Some stories are simple ice and rock drifting forever. Others might be more complex than we're ready to imagine. And that possibility raises an urgent question: if something did come looking, how would Earth fare? And that possibility raises an urgent question: if something did come looking, how would Earth fare? Because while we've been focused on Jupiter and Borisov, there's an elephant in the room. Nobody wants to address what if an interstellar object wasn't just passing through. What if one was heading straight for us? Let's talk about planetary defense. It's not science fiction. It's a legitimate field with dedicated funding and NASA personnel whose job is literally to prevent the end of the world. The Planetary Defense Coordination Office, established in 2016, exists for one purpose: identifying threats and figuring out how to stop them before they arrive. But here's the uncomfortable truth. All our planetary defense strategies are designed for objects originating within our solar system. Asteroids orbiting the Sun on predictable paths, comets we've tracked for decades, objects we can see coming years in advance. Interstellar objects break every assumption those strategies rely on. Speed is the killer. Typical near-Earth asteroids approach at around 12 miles per second. Faster than any bullet. Faster than anything humans have built. But slow compared to interstellar velocities. Oumuamua entered at 54 miles per second. Borisov at 21 miles per second. These speeds are hyperbolic. The objects aren't gravitationally bound to the Sun. They're passing through fast. Dr. Brent Barbie, who works on asteroid deflection at NASA Goddard, explained the problem. Our deflection strategies, gravity tractors, kinetic impactors, even nuclear options all require time. Years to launch a mission, years to reach the target, years for small deflections to accumulate into meaningful course changes. With interstellar objects, you might have months from detection to impact, maybe weeks. Think about the timeline. Borisov was discovered when it was beyond Mars' orbit, about 180 million miles from Earth. That sounds like plenty of warning, but it was discovered only because amateur astronomer Gennady Borisov happened to be looking in the right place, with equipment sensitive enough to spot it. If Borisov had been slightly darker or coming from a different angle, we might have detected it inside Earth's orbit. Detection time days, not months. Oumuamua was worse. We didn't spot it until after it had already passed closest approach to Earth and was heading back out. We discovered it in our rearview mirror. If Oumuamua had been on a collision course, we would have known about the threat only after impact. How big an explosion? Let's do math. A typical near-Earth asteroid hitting at 12 miles per second carries kinetic energy proportional to velocity squared. Double the speed, quadruple the energy. An interstellar object at 30 miles per second carries 6 times more kinetic energy than a solar system asteroid of the same mass. Oumuamua was roughly 400 meters long, about the size of the Empire State Building. If something that size hit Earth at 54 miles per second, impact energy would be approximately 10,000 megatons. The largest nuclear weapon ever detonated, the Soviet Tsar bomber, was 50 megatons. The Chicxulub impactor that killed the dinosaurs was about 10 kilometers across and released roughly 100 million megatons. An Oumuamua-sized impact wouldn't end civilization, but it would devastate a continent. Ocean impact, continental-scale tsunami, land impact, everything within 500 miles flattened, millions dead instantly, billions facing famine from climate disruption, and we'd have essentially zero ability to stop it, Dr. Lindley Johnson, NASA's former planetary defense officer, was frank. Our current capabilities are optimized for the most likely threats, Apollo-class asteroids with years of warning. Interstellar impactors are low probability but high consequence events we're not prepared for. The honest answer is that if we detected an interstellar object on collision course with weeks of warning, our options would be extremely limited. So what are our options? Let's walk through them. Option 1, kinetic impactor. This is what NASA's DART mission demonstrated in 2022, successfully changing asteroid Dimorphos's orbit by crashing into it. With years of warning and a slow-moving target, this works. With weeks of warning and hyperbolic velocity, the math doesn't work. You'd need such force that you'd either need an impossibly large impactor or fragment the target, creating multiple impacts instead of one. Option 2, nuclear deflection. Not blowing it up, that's Hollywood nonsense. The real strategy involves detonating a nuclear device near the surface. The explosion vaporizes surface material, and expanding vapor acts like a rocket engine. Pushing the object off course, this requires less warning time than kinetic impactors, but still needs months for mission planning, launch and intercept. Never been tested in real conditions. Option 3 Gravity Tractor. Park a spacecraft near the asteroid and use gravitational attraction to slowly tug it off course. Elegant, precise, and completely useless for fast-moving interstellar objects. Gravity tractors need years to accumulate meaningful deflection. Option 4 Pray it misses. Not a joke with detection times measured in weeks and interstellar velocities. Prayer might be our most realistic option. We could evacuate the predicted impact zone if we knew where it would hit, but predicting impact locations requires precise trajectory data we might not have time to collect. The good news? Space is big. Earth is a tiny target 80,000 miles in diameter in a solar system trillions of miles across. The odds of any given interstellar object hitting Earth are astronomically small. The bad news? Astronomically small doesn't mean zero, and with thousands passing through the inner solar system every year, eventually one will have Earth's name on it. Dr. Amy Mainzer, Principal Investigator for NASA's Near-Earth Object Wide Field Infrared Survey Explorer, focuses on detection. The best defense is early warning. The more time we have, the more options we have. We need better detection systems, space-based infrared telescopes that can spot dark objects against darkness. We need international coordination so observations immediately get shared globally. And we need rapid response mission capabilities spacecraft on standby that can launch within days, not years. That rapid response capability doesn't exist yet. The fastest we've launched a planetary mission was New Horizons to Pluto, which took about a year from final approval to launch with years of planning beforehand. Developing standby spacecraft with mission-ready teams would be expensive. Convincing governments to fund preparation for low-probability events is politically challenging. We've faced this risk assessment before. Pandemic preparedness, nuclear accident response. Asteroid impact is similar low probability, high consequence, requiring expensive preparation for an event that might never happen. COVID-19 showed us the cost of inadequate preparation. The question is whether humanity will take planetary defense seriously before we need it, or only after the first impact. There's another angle. What if the threat isn't accidental? What if an interstellar object were deliberately aimed? This veers into speculation, but it's not physically absurd. An advanced civilization capable of interstellar travel could certainly accelerate objects to impact velocities. Dr. Philip Lubin from UC Santa Barbara points out, relativistic kill vehicles, projectiles at substantial fractions of light speed, represent a theoretical weapon that's terrifying because of its simplicity. You don't need explosives. Kinetic energy alone is devastating. A 1 kilogram projectile at 90% light speed carries more energy than the largest nuclear weapons. And you'd have essentially no warning by the time you detected it. Impact would be seconds away. The good news? There's no evidence anyone's shooting at us. The better news, physics makes this extremely difficult, requiring energy likely only possible for highly advanced civilizations. And there's no reason to think any such civilization has hostile intent. But Borisov's pulse reminds us the universe can surprise us. Objects we thought we understood can behave unexpectedly. Our planetary defenses, designed for threats we know, might be inadequate for threats we haven't imagined. Earth is more vulnerable than most realize, and closing that vulnerability gap requires resources, technology, and international cooperation we're only beginning to develop. Which brings us to the most important question: what have we actually learned from Borisov, and what happens next? Which brings us to the most important question: what have we actually learned from Borisov? And what happens next? Because after all the speculation, all the analysis, all the sleepless nights spent by astronomers poring over data, we're left with something both frustrating and exciting, more questions than answers. Let's start with what we know for certain. On March 3rd, 2020, interstellar object 2/Borisov emitted a 41-second electromagnetic pulse detected across multiple wavelengths by observatories worldwide. The pulse was directional, strongest toward Jupiter's position. The energy levels exceeded anything we typically associate with cometary activity. No subsequent pulses were detected despite extensive monitoring. Borisov continued its journey out of the solar system and is now beyond our ability to observe. Those are the facts. Everything else is interpretation, hypothesis, educated guessing. What have we learned first? That interstellar objects are more complex than we initially thought. Before Oumuamua, we assumed interstellar visitors would behave exactly like solar system comets, just from somewhere else. Oumuamua challenged that assumption with its bizarre shape and unexplained acceleration. Borisov looked reassuringly normal until it didn't. The lesson: we can't assume anything about objects that spent millions of years in environments we've never directly studied. Interstellar space might alter comets in ways we haven't anticipated. Cosmic ray bombardment, interstellar dust impacts. Extreme cold, these conditions could create internal structures or chemical states that produce unexpected behavior when the object encounters a star's warmth. Second, we've learned our detection capabilities are inadequate. We're finding maybe one interstellar object every couple years when thousands are passing through. That's not a detection system, that's accidental discovery. The Vera Rubin Observatory will help enormously when it comes online, but even that will catch only the brightest, largest objects. We need space-based infrared telescopes specifically designed for detecting dark, fast-moving objects against the background of space. NASA's NEO Surveyor mission, planned for launch in 2027, will help, but it's optimized for asteroids in solar orbits, not hyperbolic interstellar trajectories. Dr. Danica Remy, president of the B612 Foundation focused on planetary defense, emphasizes the urgency. Every interstellar object we detect teaches us something about the galaxy beyond our solar system. But more importantly, better detection means better warning if something dangerous is heading our way. We're talking about existential risk management. The investment required is minuscule compared to the potential consequences of being caught unprepared. Third, we've learned that international cooperation in astronomy works but needs improvement. When Borisov's pulse was detected, observatories worldwide shared data rapidly. Scientists from dozens of countries collaborated on analysis. That's encouraging, but the response was reactive, not proactive. We need coordinated monitoring systems with automated alerts, rapid response protocols, and dedicated resources ready to deploy when something unusual happens. The James Webb Space Telescope, Hubble, Chandra. These are booked months or years in advance. When an unexpected event occurs, getting observation time means bumping other critical science. We need reserve capacity specifically for transient, unpredictable phenomena. What happens next? Several missions are in development that could revolutionize our understanding of interstellar objects. The Comet Interceptor, a European Space Agency mission scheduled for launch in 2029, will wait in space at the Sun-Earth Lagrange point L2, ready to be dispatched to intercept a newly discovered long-period comet or interstellar object. Is the first mission designed specifically for rapid response to unpredictable targets. If another Borisov appears, Comet Interceptor could actually reach it, analyze its composition, photograph its nucleus, and maybe provide answers about what caused that pulse. Project Lyra, proposed by the Initiative for Interstellar Studies, goes even further. It's a conceptual mission to catch up with Oumuamua using advanced propulsion systems, solar sails, gravitational assists, maybe even fusion engines. The engineering challenges are immense, and funding doesn't exist yet. But it demonstrates that scientists are thinking seriously about not just observing interstellar visitors, but actually pursuing them. Breakthrough Starshot, the initiative to send tiny spacecraft to Alpha Centauri at 20% light speed, has implications for interstellar object research too. If we can accelerate spacecraft to those velocities, we could theoretically launch fast-moving probes to intercept interstellar objects while they're still in our neighbourhood. Launch windows would be narrow, but the payoff detailed analysis of an interstellar visitor would be extraordinary. Dr. Sarah Seeger from MIT, who works on exoplanet characterization, sees interstellar objects as cosmic ambassadors. Every interstellar object carries information about its home system. If we could analyze enough of them, measure their composition, study their structure, understand their formation, we'd essentially be doing comparative planetology across the galaxy. We'd learn whether our solar system is typical or unusual, whether the chemistry that led to life on Earth is common or rare. These objects are free sample return missions from other stars. We just need to study them properly. But there's also the uncomfortable question we can't entirely dismiss. What if some interstellar objects aren't entirely natural? I'm not talking about alien spacecraft that remains wildly speculative and unsupported by evidence. But what about objects that are mostly natural with artificial components? A comet carrying a small instrument package, for example, would look almost entirely natural. Only close-up examination would reveal anything unusual. Dr. Avi Loeb continues to advocate for taking this possibility seriously. Science progresses by exploring unlikely ideas, not by declaring certain questions off limits because they seem uncomfortable. Should we assume every interstellar object is natural? Of course. Should we check also? Yes. If we'd examined Oumuamua up close and found it was purely natural, that data would have been valuable. The fact that we didn't get close enough to definitively rule out artificial components is a missed opportunity. Here's what's certain: more interstellar objects are coming. As our detection improves, we'll catalogue dozens, then hundreds. We'll start seeing patterns. We'll understand which characteristics are typical normal outgassing, standard compositions, predictable behaviour, and which are genuinely anomalous. Borisov's pulse will either emerge as a one-time fluke or as an example of a previously unknown class of phenomena. The next interstellar visitor might be the key. If it also emits electromagnetic pulses, that suggests a natural mechanism we don't yet understand, perhaps something related to interstellar material accretion, cosmic ray damage, or subsurface volatile pockets. If the next 1,000 interstellar objects show no such behaviour, Borisov becomes even more mysterious, an outlier requiring special explanation. What about Jupiter? The solar system's giant continues its orbit, its magnetosphere churning, its radiation belts pulsing, its great red spot swirling for centuries. Did it notice Borisov's pulse? Did its magnetic field respond? We don't know because we weren't watching closely enough. But we're watching now. Future interstellar object encounters will have dedicated Jupiter monitoring UV telescopes tracking auroral activity, radio observatories listening for emission changes, magnetometers on Juno measuring field variations. We won't miss it again, and perhaps most importantly, Borisov reminded us that the universe doesn't care about our comfort zones. Nature routinely produces phenomena that challenge our understanding. Black holes that shouldn't exist according to stellar evolution models. Galaxies moving in ways that require dark matter, something we can't see, can't detect directly, but know must be there. fast radio bursts that seemed impossible until we found their source. Science advances not by confirming what we already believe, but by confronting observations that don't fit. Borisov's pulse doesn't fit. Not comfortably. Not yet. Maybe it never will. Maybe we'll develop a complete natural explanation that accounts for every detail. Or maybe Borisov will remain one of those cosmic mysteries that keeps astronomers up at night, wondering what they witnessed. But here's the beautiful part: we're asking these questions. We're developing the technology to find answers. We're preparing for the next discovery. Humanity spent 300,000 years looking at the night sky, wondering what's out there. Only in the last few decades have we developed tools capable of actually finding out. We're the first generation in human history with the ability to detect visitors from other star systems, analyze their composition, track their paths, and maybe eventually visit them ourselves. So when you look up tonight at the stars, remember that between these points of light, through the darkness, objects are travelling. Some are chunks of ice and rock, mindlessly drifting. Some carry stories written in chemistry and structure, messages from stellar systems we'll never visit. And some perhaps are more than they appear. We're watching now, we're listening. And when the next interstellar visitor arrives, we'll be ready. Not with all the answers, science never promises that, but with better questions, better instruments, and a growing understanding that our solar system isn't an island, it's a waypoint, a rest stop on routes travelled by objects we're only beginning to discover. Borisov came, it pulsed, it left, and it changed how we see our place in the galaxy, not as isolated observers, but as participants in a universe far stranger, far more connected, and far more mysterious than we ever imagined. The journey of discovery has only just begun, and the next chapter is already approaching through the darkness, waiting to be found. What will we discover when it arrives? Nobody knows, but that's exactly what makes it worth watching for. So there you have it, the story of 2I/Borisov, an interstellar comet that looked perfectly normal until it didn't. 41 seconds that challenged everything we thought we understood about visitors from beyond our solar system. A pulse aimed at Jupiter that nobody can fully explain. And a reminder that the universe is under no obligation to make sense to us. Was it natural? Almost certainly. Was it fully understood? Not even close. And that's exactly why stories like this matter. Because every mystery solved opens 10 new questions. Every answered what leads to a deeper why. That's not a flaw in science, that's the entire point. We're not here to have all the answers. We're here to keep asking better questions. The night sky isn't a painting. It's a living, breathing, constantly changing frontier where objects from other star systems pass through our cosmic neighbourhood, where planets hum with electromagnetic energy, where mysteries arrive unannounced and leave us scrambling for explanations. And we get to witness it. We get to be the generation that finally has the tools to explore these questions seriously. If this story fascinated you, if it made you look at the night sky a little differently, share it with someone who'd appreciate the mystery. Leave a comment. I'm genuinely curious. Do you think Borisov's pulse was purely natural? Or is there room for alternative explanations? What would you ask if you could study the next interstellar visitor up close? Until then, keep looking up. Because somewhere out there, between the stars, the next visitor is already on its way, and when it arrives, we'll be watching. Good night, sleep well, and remember, you're not just standing on a planet. You're travelling through a galaxy full of secrets waiting to be discovered.